Howdy, we are Team Daggr, and today we would like to present to you Bell 2.0. Before we begin, we would like to introduce ourselves.
I'm Alan Liu. I'm the electrical engineer.
I'm Dale Hedger, the software engineer.
I'm James Kynard, the mechanical engineer.
I'm Jonathan Guyton, the systems integration engineer.
And I'm Casey Juarez, the project manager. Our advisor and sponsor is Dr. Crosby. Today, we will give a bit of a background with our project, a brief overview of our project, continue with the mechanical, electrical, software design, and at the end, we will conclude with the project status and logistics. Let's begin. A bit of background. As of right now, there are many autonomous vehicle platforms that don't require human intervention to navigate through urban environments. They can do so with the combination of pre-existing knowledge of the environment and high-cost sensors to navigate locations successfully. They do path planning through resource-intensive processing of large amounts of data from sensors instead of using pre-existing knowledge through a mapping application. The problem is that there isn't a system that seeks to bridge this gap of an autonomous vehicle which is cheap and able to navigate with pre-existing information. There is a need to work towards creating a low-cost technology demonstrator for navigating urban environments. Daggr's solution is to develop a robust autonomous robot guide that will take users to the desired locations. This autonomous robot will be called Bell 2.0. Bell 2.0 will use Texas A&M University as a testing location to act as a navigating guide for students, faculty, and visitors. The user will ask Bell 2.0 to take them to a specific area or building on campus, and Bell 2.0 will then drive to that location, leading the user. Bell 2.0 will utilize obstacle avoidance, speech recognition, cellular communication, and GPS localization to achieve this goal.
So beginning with our project overview, we'll get into our concept of operation. So for our concept of operation, a user will walk up to the Veil 2.0 robot and speak into the microphone and choose one of the options available on campus for the Veil 2.0 to navigate them to. Veil 2.0 will then automatically chart a walkable path for the person to follow and take them to a building or site. Getting into our functional requirements, on our hardware side, we are planning to upgrade our suspension system. We are taking the previous Veil 1.0 Scuttle robot design and implementing a new robust aluminum frame. We're also incorporating adequate housing for electrical components. This is done with an acrylic electrical box. For software, we'll be implementing edge detection, obstacle avoidance, and reaching our destination. These are achieved by using our OAK-D camera for edge detection, our LiDAR for our obstacle avoidance, and ArcGIS navigation system to reach our destination. Our data and communication requirements is speech recognition for when the user speaks to Veil, so we can tell where it's going, and real-time live feed of the main program. And for power, we'll be creating a battery management system.
So for the conceptual block diagram, we essentially have the user and the base station on the bottom left-hand side of the CBD. And this communicates to the robot using a communication protocol called Navlink. And on the robot, there are three layers: the intelligence, the sensing, and the actuation layer. In the intelligence layer, we have the Raspberry Pi, the Pixoc Orange Cube, and a 4G modem. The sensing layer, we have the RTK GPS, the OAK-D camera, and the LiDAR, and the microphone. And for the actuation layer, we have the motors, the motor driver boards, and the speakers. And the robot communicates to the base station through internet over cellular. And the base station is running software called Q Ground Control, which is integrated with the Pixoc flight controller board. This is our functional block diagram. We have the three aforementioned layers: the intelligence layer, the sensing layer, and the actuation layer. We also have a power distribution block and a base station block. As you can see, the sensing layer has the GPS, the depth camera, the lidar, and the microphone. The actuation layer has the motors and the motor drivers, and the intelligence layer has the Raspberry Pi and the flight controller board. Taking a closer look at the intelligence layer, this is a general overview of how it functions. So the base station computer communicates to the robot over internet. We create a virtual LAN network using a service called Zero Tier. And they talk to each other through a UDP socket. The Raspberry Pi acts as the companion computer for the PX4, and it communicates to it through the communication protocol called Mavlink, and it has a 4G modem attached to it through USB. And the ground station talks to the robot also through Mavlink, which is facilitated through internet. And this is a more detailed view of the functional block diagram looking at the intelligence layer.
Now for the mechanical design. So here are CAD models for the robot. The robot is entirely made out of aluminum tube stock. This provides a lot more rigidity as compared to the Veil robot. The picture on the left, you can see there are the 4 wheels, and then there are 2 motors driving 2 wheels each. And so everything in here is incredibly well constrained. It's very rigid and robust, which is what we were going for. And then there is the blue box on top of that where all of the electronics are housed, and that is put under suspension. So as the robot moves over the ground, it won't actually have the electronics also bouncing along with it. They will be protected from all of this vibration. And then the pole on the right is the sensing pole. So this is where our camera will be mounted so that we have a higher view. So we're actually kind of looking down instead of looking straight on, and that will improve our ability to do computer vision. The wheels are rubber, pneumatic wheels, and so that will also provide an additional layer of damping. So moving on to our features as compared to BAST, as already said, we have a full aluminum frame. There's internal damping for the robotics, or the electronics for the robot. The wheels are substantially larger. So the wheels on our robot are 8 inches, whereas BAST's wheels were 3.5 inches. This means that whenever you go over a crack, there's a lot less jitter, which will help for computer vision. And then we have substantially stronger shafts and bearings because BAST had a problem of consistently breaking their shafts and bearings, so we are fixing those. And then we have our sensor pole for better camera placement. Here is our a picture of our dry fit frame. That's a Nalgene for scale. So this whole robot is approximately 27 inches wide by 18 inches long. So it's pretty big, and we've been putting all of this together. We should get it done in its completion pretty soon. Onto the electrical design.
The electrical design, we'll take a brief look at our alpha schematic. This is an alpha schematic for our power distribution, which is the only purpose of our PCB.
For our software development, the way we have all of our scripts organized is within a hierarchy. So starting at level 1 is where all of our low-level programs for each sensor is. This is our GPS, our LiDAR, camera, motors, encoders, etc. Then we determine what type of function that they will be used for, and they will go into our second hierarchy of scripts. This is our bearing compass, the NID control, optical avoidance, and our speed. Level 3 incorporates all of these level 2 scripts and makes both what are called the movement scripts and the user interface scripts. And eventually, they will both all be put into our main script, which is where all the programs will be running in sync with each other. For our alpha design, where we first start off is with our voice command. A person will walk up to the robot and tell it, take me to this building. And so that speech will be interpreted to a text, a keyword will be detected by the speech recognition API. If it is determined successfully, what it will first do is it will obtain the current GPS coordinate of the robot. After doing this, it will chart a path based on the building that the person wants to go to and the RTS waypoint that's been set for the location. And from this, it will start the movement commands all along the charted path. So the first one to start off that it will do is the LiDAR detection. So the LiDAR will keep reading. If an obstacle is detected, it will maneuver around it using obstacle avoidance algorithm that we've made. And as it is completed, it'll just circle back. And then in a case that it needs to set down all the others, it will enable the GPS and bearing script again. And for this script, it will start off by reading the GPS position and bearing compass. So which way is the robot pointing compared to the actual Earth compass of north and south. It will calculate the degrees needed to face the bearing compass to the next waypoint. And then it will use PNID control to stay along the path. And then it'll loop back around. For the onboard voice command, what it will do is it will text keywords at any moment. And so it will determine speech to text. And if the command is valid, say, for instance, if we want the robot to stop, it will terminate all movement commands, disable all the other programs, and will wait for a new command. And it'll start back up again. For our camera edge and obstacle avoidance, what it will do first is it will read an image frame, then it will go through an image processing, then we will run it through the edge detection process. And from that, we will make the correction, and if it is detected, we will calculate the angle adjustment based off of the image data, use computer vision PNID control, and then make sure that is complete. And after that, it will re-enable some of the other programs, as well as obstacle avoidance. Specifically, the speech recognition, what that looks like is it will start at the beginning, it will activate the mic, it will listen for a keyword, and when that keyword is given by the person, it will process the data through an API, and it will verify that the command that's given matches with its list on the script. And when that is given, it deactivates the mic, compares it to list, and if the answer is acceptable, it will send that to the rest of the script. Getting a little bit deeper, for the movement algorithm in the level 3 hierarchy, it will start the movement. If it has not arrived, then what it will do, it will read the GPS coordinates in the magnetometer, then it'll read the image pavement edges and data, then it will adjust the heading angle to face where the next waypoint is. Read the bearing compass, calculate the robot theta direction offset, and based off of these degree numbers that we've determined, it'll determine how sharply the robot needs to turn, if at all. So we have a larger turn sequence and a smaller turn sequence. And so for the turn sequence, we read the rotational velocity, and the linear velocity offset is 0. We apply inverse kinematics to make both motor profile adjustments per wheel, and then update current wheel velocities within the target velocities that we set. For the forward sequence, what we do is we set the theta direction offset to 0. Linear velocity is equal to 1 foot per second. Apply inverse kinematics, update the PNID control variables, implement obstacle avoidance, and use KP and KPI variables except for the motor velocities. And then we had a small delay. More of a pictorial representation of the movement algorithm, and along with the other programs. The robot has its own internal north-facing compass, but what it will do is it will try to align itself with the next waypoint. And the distance between where the robot detects the next waypoint and its own north compass, it will create an angle. And this will be our offset. And this is exactly what the robot will try to adjust to face towards. And what this will look like in our video feed is what you see on the right using DepthAI and OpenCV. It'll create edges on the sides of the sidewalk. It'll point its own north compass along with where the next waypoint is.
This is a demo of the edge detection model that we have used
along with the OAK-D camera, we wrote a script to display the video stream with the post-image processing, and you can clearly see the major edges in the video, and we plan on using this with other libraries to keep the robot on the sidewalk. Here's a demonstration of Q Ground Control, which is the base station software used to communicate and control the Pixhawk flight controller. As you can see, as I move the Pixhawk, here's moving the heading, and then roll and tilt. The Pixhawk is a self-contained IMU, so it has all those sensors. And for path planning, we can upload a path that we create ourselves using whatever algorithm that we make, and the robot will traverse along that path.
Here we are showing Daggr's schedule overview. We have broken it down into 4 different statuses. As you can see, the alpha hardware and alpha code are late. The reasoning behind this is that we're missing a crucial order that we still have not received. Without this order, we cannot complete the robot. Here is our Gantt chart. In our Gantt chart, you could see that we have broken down into different sections, and in their sections, there's different tasks. For the documentation, we are continuing to work on it, and we won't complete it until the due date, which is December 8th. For the alpha design, we will complete it by November 9th. For the beta design, we will start on October 18th, and we should have it completed by November 29th. For the final design, we'll begin on November 22nd, and we should have it completed by December 6th. Here is our labor status. In our labor status, we have predicted for the total to have 70 hours. What we actually got was 82.92 hours completed. And for next week, we assume we will complete 93 hours. Here is our financial status. When we estimated the total that Daggr will spend on Vel 2.0 for the SCP, we assumed we would waste a total of $2,308.74. Currently, we have estimated that we will spend a total of $2,902.01. The reasoning behind this increase is that the majority of our materials increased their cost due to COVID-19. As of right now, we spent a total of $2,022.15. That is the end of our presentation. Thank you for listening. If you have any questions, please feel free to email us.